Okay, now we're on to the Jovian planets, or the planets you might refer to as the gas giants, the largest planets in our solar system. And we'll start with the similar table to what we had before, but with those Jovian planets added. We'll go through things here a little bit more quickly for a couple of reasons. One, we can build on the ideas we had before, but also we know a little bit less about these planets. They're further away, they're less like the Earth, they're a little harder to study. But let's take stock of some of the important differences. First, if we look at mass and radius, the outer planets, Jupiter, Saturn, Uranus, Neptune, much, much larger, right? So Jupiter 10 to the 27, Earth 10 to the 24. So Earth is the largest terrestrial, and Jupiter is about 1,000 times bigger in terms of mass. In terms of radius, you could go there as well. So compared to Earth, Jupiter is 11 times the radius of the Earth. Now, in terms of density, they are much lighter. So these are not planets that are primarily composed of rock and metal. Even though they're much more massive and larger, it's not because they have more rock and metal material in them. It's because they're made up of so much gas, in particular hydrogen. So these planets are largely composed of hydrogen gas, so much that their size is enormous and their mass is enormous, but their average density is actually lighter, much lighter. If you remember in the last video, I said that 1,000 would be water. So these are just a little bit heavier than water, except for Saturn, which is lighter. If you had a bathtub big enough to put Saturn in it, it would float, right? So if it's lighter than water, less dense than water, it would float. So Saturn would technically float in water. Surface gravity, that varies. Jupiter has stronger gravity. Now, there's a couple of things going on here that affects the gravity of a planet. One is how much mass, but also its size, right? So if you get farther from the center of the planet, gravity gets weaker. But if you have more mass inside, it gets bigger. So there's competing effects. And for Jupiter, the way it balances out is its gravity is actually stronger, even though you're farther away from the center. And Saturn is about the same, Neptune is about the same. So these two planets would have similar gravity, and Uranus is not that much different either, but Jupiter's is noticeably stronger gravity. You feel a lot heavier. That's going to be tied again to the escape speed. Stronger gravity meaning you need more escape speed to leave the planet. Rotation period. So for the Jupiter and Saturn, they're actually rotating more quickly than the Earth. So one day on Jupiter or Saturn is less than half a day on the Earth. So they're much larger, but they're also spinning faster. And Uranus, you'll notice again, has another minus sign. Like Venus, it's rotating the opposite direction. And it's very extreme. If you look at the tilt of its orbit, 98 degrees. So it's almost tipped on its side. So that's its axial tilt. So there's going to be times of the year, if that axis is of its year where it's pointed towards the sun, its axis is pointed towards the sun. It's an extreme axial tilt. Jupiter, not much of an axial tilt. Saturn and Neptune, not too different from what we would experience on the Earth. Surface temperatures, these are all much colder, due to their distance from the sun. The further they get away, the colder the planet is. And then this last column here, magnetic fields. We'll talk a little bit about that in particular for Jupiter. It has a very strong magnetic field. And when we talk about the sun, we'll come back to the importance of magnetic fields of planets. So just hold on to that one for now. All right, so here we have a size comparison image and another one here. You can see the Earth is dwarfed by these other gas giants, these Jovian worlds. Now we're going to take our tour of each one individually. So we'll start with Jupiter. When you see Jupiter through a telescope, a reasonable telescope, not like a fancy NASA instrument or anything, but something you could buy as an amateur astronomer, you'll notice some features. The primary feature that you'll notice is that it has bands of different colors in it. So you'll see some structure. And it won't be as clear as this, but you'll see bands of light and dark, reddish, orangish color. The bright areas we call zones, and the dark area we call belts. Okay, so it has zones and belts. The zones are cooler, they're higher up, and so the belts are like sunk deeper into the atmosphere. Those darker regions are sunk into the atmosphere a little bit. And then underneath them, we get zonal flow. Now, what's interesting about these zones and belts is that they're spinning around the planet in opposite directions. And so because of that, there's going to be friction in between them, and that causes the possibility of storms to develop. And the most notable feature of Jupiter, the most famous feature of Jupiter, is the Great Red Spot. Okay, so that's pictured here. And so we have gas flow here going this way, gas flow here going this way, and that's caused this hurricane to form. So that's what the Great Red Spot is. It's essentially a hurricane. It's a hurricane that's about the size of the Earth. So the Earth would fit inside the Great Red Spot. It's not the only one. Any of these round regions you see on Jupiter are different storms. And here you can see one storm as it approaches the Great Red Spot and then disappears. So the Great Red Spot is a hurricane that actually can consume other hurricanes. And it's been there for a long time, as long as we've been taking pictures of Jupiter. What we know about Jupiter is due to our observations, but also we have put things in orbit around it and sent a probe down through its atmosphere. That was called the Galileo probe, and it was in 1995. The arrow here indicates where it was inserted into Jupiter's atmosphere. And that's given us the information about what's beneath the surface, helped us to understand the layers of clouds, because what we see is really only the top layers and not what's inside. Now, if we take a look here at these layers, and we can compare Jupiter to Saturn. So these are Jupiter's cloud layers and Saturn's cloud layers. Oh, didn't mean to do that. We can see that there are some similarities. Stratosphere, ammonia ice layer, haze, troposphere, ammonium hydrosulfide, water ice. So the layers are similar, but there are differences in thickness, and exact composition will change. Because they have no solid surface, the scale here is set so that 0 corresponds to the top of the troposphere. So this is like the upper atmosphere, and this is the surface of Jupiter, the surface that we see, and this is below the surface that we see. And same thing for Saturn. 0 is the top of the troposphere. Saturn's cloud layers, the big difference between it and Jupiter is it's actually much thicker. And so we see the banding on Jupiter a little bit more obviously, the difference in colors, difference in coloration, because its cloud layers aren't quite as thick as Saturn. Now for Saturn, the most obvious feature is obviously the rings. And our view on the rings changes. So when you look at Saturn, you might see it with the rings aligned, like here on the lower left, in your line of sight. So they look very thin, and the rings are very, very thin. Or it might be tipped up and away from you. Now, when it's tipped up like this, or like this, it's when Saturn is the brightest, because those rings are reflecting so much sunlight. And so here's a nice picture through a smallish telescope of what Saturn might look like. If the rings are aligned like this, so that you're kind of looking at them at an angle, Saturn can be really, really bright. It's still bright when the rings are like this, but its brightness is lessened a little bit because you're not getting so much light from the rings. And it does change over time, obviously. So here is 1996, 97, 98, 99, 2000. And this was 95. So it's gone from, just a thin line that you see up to here, where you get to kind of the fullest extent of the rings. So Saturn's atmosphere is similar to Jupiter's, and if you look at this picture, it looks like a picture of Jupiter. But this is in infrared. This is not what we get to see in visible light. This is infrared. It penetrates through the atmosphere layers a little bit more and gives us more detail. And so this is a false color image. But when we look at it this way, it does look a lot more like Jupiter, and we can start to see the similarities in their atmospheric structure. And we can see things like storm systems. So here, storm systems. Again, this is an infrared image. And we can see the banding structure on Saturn. All right, now let's finish with the last two planets, which we know the least about. I have the least to say about Uranus and Neptune. In visible light images, they really look like blue marbles with not a whole lot of structure. But if you look a little bit closer and study these, there is some detail. They do have some similarities to Jupiter and Saturn in that they have storms. So this is believed to be a storm on Uranus, taken over a sequence of a time sequence. But mostly it's featureless. The most interesting things about Uranus that we know are that its axis is completely tipped over. All right, so here's the timeline here. So 1986, Uranus is almost pointed towards the sun. Here it's pointed, this is sort of pointed along its direction of orbit. This is pointed away from the sun, kind of back against its orbit. And so it has the most extreme axial tilt of any planet. And the other thing is that it also has a ring system, and you can see it in infrared that it has a ring. Now Jupiter also has a ring. It's even fainter. In terms of outer planets and their rings, Saturn has obvious, the most dramatic ring system. Jupiter has a very thin one that we can barely make out in infrared, and Uranus has one that's obviously visible in the infrared, but not quite so much in visible light. And now for Neptune. Now Neptune, like Uranus, was mainly featureless. It did have, in our first good pictures of the planet taken with the Voyager mission, a big storm on it, which was called the Great Dark Spot. And so that was the Voyager mission image, and the picture looked like this. And here's a close-up of what the Great Dark Spot looked like on Neptune. Now the Voyager mission could get this level of detail because it was sent out into space to get closer to it. We cannot see this detail with a good telescope. And in fact, this storm appears to have disappeared. And when we take pictures with the Hubble, we get this resolution here, 96, 98, 2002. So our telescopes now don't see that storm anymore. So it's apparently disappeared off the surface. But there are bands, and so there's probably similar atmospheric structure to all of these outer Jovian planets, this rotation of the gases in zones and belts. Although we don't know a lot, we haven't sent things out to explore into Uranus or Neptune. We've done some extensive studying of Jupiter and Saturn, but not yet out so far to Uranus and Neptune. So we know the least about those two of the planets.